Hello, welcome back. Today we're going to be taking a look at the natural log function and its derivative. To start though, the natural log function, the natural log of x, is the inverse of our function e to the x. If we wanted to graph it, you might remember that I know that the natural log of 1 is just 0, that the natural log of e is going to give us 1. So I can kind of graph it. There's 0, and the natural log of e, which is a little bit before 3, is up here, and it's going to give us a value of 1. The y-axis acts as an asymptote. So for the natural log of x, x has to be greater than 0. And we can kind of see that when we look at the function. If I want to say if x was 0, we would be saying that we would be saying that there is a power e to some power that would make y equal 0, and that's not going to happen right there. So x equals 0 acts for us as a vertical asymptote, and that's what our natural log function will look like right here. The domain is going to be from 0 to infinity, but the range, because we can't be 0, we can get all the way close to 0 as we can, that goes from negative infinity to positive infinity. It just keeps growing. This is what we consider a continuous function, so it just goes on and on and on. It is also what we call one-to-one. So one-to-one function, it says for every x, if you forgot, for every x, there's exactly one y. And this is a function that goes concave down. We're going to be spending a little bit more time with this when we get to our derivative tests. Some other properties, so that's the kind of review of what natural log looks like. There are some other properties. If a and b are positive and n is rational, then we can say the following. One, we already talked about these, that the natural log of 1 is 0 and the natural log of 1 is e. These are the properties that we use to expand and condense. These are the ones that we really want to use today. If I have the natural log of a times b, that's just the natural log of a times the natural log of b. And where these come from is it's the exponent. These come from our exponential rules. Remember, we're talking about the base e. So if I have something like 5 to the a times 5 to the b, if I'm multiplying the same bases, my rule says I can add those exponents. And that's, remember, what we're doing. We're adding the exponent, because from our rule up here, a natural log is just the exponent itself. So the natural log just becomes our exponent again. And if we have the natural log of a over the natural log of b, we're saying that we can subtract their powers. And again, if I'm dividing 5 to the a over 5 to the b, my rule was I could subtract their powers, 5 to the a minus b. And likewise, and our last one is a to the n becomes n to the natural log of a. We can just drop our power. And again, that comes from our rule. If I have 5a to the b, my rule says is I can multiply. I can write this as 5a times b to the a times b. These are the rules that we want to be able to use today. They're going to help us with our derivatives. So for our first one, we want to write as a sum or difference. So what they're asking us to do here is, of course, is to expand. And if I wanted to expand this, I'm just going to rewrite it. This is going to become the natural log of x cubed minus 2 over x to the 4th to the 1/3. Now, I can write this 1/3 to both of my power, on my array. So, we want to expand this. So, I'm going to leave this 1/3 out here, but I'm going to look at the inside. For the inside, I can write the inside as just the natural log. Because I'm dividing, I can write this as a subtraction problem. The natural log of x cubed minus 2 minus the natural log of x to the fourth. All of that to the 1/3. Now that's okay for expanding, but I can go one step further by looking at the x to the fourth. I can still expand this. I can use my power rule. My x to the fourth, I can just drop my power. So not much more, but it will help us later on, we'll see. The natural log of x cubed minus 2 minus, this becomes now 4 natural log of x, all of that to the 1/3 power. Be careful, that's as far as we can really expand this one. You're going to want to say, oh, well, I can distribute this. No, we cannot. Just leave that alone. If I want to write as a single log, now I just want to do the opposite. So I want to do the opposite. So I'm going to use my power rule right here, and that's going to give us the natural log of x plus 3 squared plus the natural log of x minus 2. Raise that to the 1/2. We get 1/2 right there. So I'm going to do my powers, and because I'm adding, my rule says if I'm adding, I can write this as a multiplication problem. We would get the natural log of x plus 3 squared times x minus 2 to the 1/2. And there is our condensed form. When we solve natural logs, we are going to use the inverse property. And the inverse property says if and only that y equals the natural log of x if and only if e to the x equals y. This is our inverse property. But really, we don't ever do this, honestly. We use something called, we just want to get rid of the base. So I am going to exponentiate. This is kind of a big word for us in mathematics. It's called exponentiation. Exponentiate. And really what it means is turn everything into an exponent. I think of base. Well, what's the base of the natural log? Well, it's just e. So I can write this as e. But if I e this side, I e the other side. And we get e cubed. Thank you, I do work out. Now, it just so happens, because e and natural log are inverses of each other, they will cancel out. For example, if I were to plug this in, if I were to write down the natural log of e to the x, you should remember this as just being x from last year in your pre-calc class. They cancel each other out because they're inverses. They just cancel each other out. So that's why this is so nice. I'm going to get this e cubed here, but this e and this natural log cancel each other, and I get x minus 3. So therefore, we can say x is equal to e cubed plus 3. We're going to do a lot of this later on this year, okay? All right. So let's see here. So let's talk about the calculus of it. And when you go into the next video, we will start that. I'll see you soon. Bye-bye.